For bosses purchasing plane tickets or aircraft, the brand is a crucial factor. Whether it's Boeing, Airbus, Comac, or Embraer, Bombardier, Dassault, each brand has its own characteristics. But have you ever wondered if these aircraft are actually made by them? In reality, for modern commercial aircraft, from small kitchen seats to large engines and avionics, nothing is made by the aircraft manufacturers themselves. Rather than saying they're building aircraft, it's more accurate to say they're assembling them. So in this year's Civil Aviation Entry Series, I'll show you all at once how the aircraft you're placing massive orders for are actually made. If Boeing and Airbus don't build aircraft with their own hands, who are the real heroes behind each commercial aircraft? To explain the entire aircraft manufacturing process clearly, we need to introduce the world's largest aircraft manufacturer, Boeing. Initially, Boeing did indeed work with its own hands, managing every detail. Taking the Boeing 747 as an example, except for engines from Pratt & Whitney, most parts were made by Boeing itself. To build this massive aircraft, Boeing specially constructed the Everett factory, the world's largest single building, covering nearly 400,000 square meters and employing over 40,000 workers, single-handedly boosting employment in Seattle and creating America's golden age of manufacturing. But as the aviation industry developed rapidly, this approach began to strain. Although later commercial aircraft weren't as large as the 747, the introduction of advanced materials and increased electronic equipment made each aircraft far more complex than before. The massive R&D costs were difficult even for Boeing to bear alone. Meanwhile, airlines buying aircraft and governments also viewed Boeing with envy, asking why should our money create jobs and tax revenue for you? If building an aircraft can provide employment for tens of thousands of workers, shouldn't we get a piece of it? With this background, both sides saw eye to eye, with other countries wanting a share of the pie, and Boeing willing to share the risks. Thus, in the 1990s, Boeing took its first step in transformation. When developing the 777, Boeing unprecedentedly brought in 8 airlines from different countries to participate in design and was the first to abandon traditional blueprints, fully adopting CAD, CATIA, and other software, making the 777 the world's first commercial aircraft with full 3D digital design and virtual assembly on computers. All these efforts had one purpose: to pave the way for subsequent large-scale outsourcing manufacturing. Also starting from the 717, suppliers from Japan, Australia, and Europe gradually joined Boeing's supply chain. The subsequent Boeing 787 is the culmination of outsourcing and risk-sharing. A major highlight of the 787 is that over 50% of its fuselage uses composite materials. But Boeing itself had no experience in large-scale carbon fiber production, so it entrusted this key task to Toray, the global leader in this field from Japan. Meanwhile, Fuji Heavy Industries, Mitsubishi Heavy Industries, and Kawasaki Heavy Industries also became core partners, sitting at the table with Boeing. Later, China's Chengdu Aircraft Corporation also joined, responsible for the 787's rudder. That's right, Chengdu can not only build the J-20 and 6th generation fighters, but also the Boeing 787. Ultimately, in the 787's total engineering workload, Japan contributed 35%, Australia, Italy, China, Europe, and other countries accounted for 35%, while the United States itself only accounted for 30%. Rather than calling this an American aircraft, it's more accurate to call it a Japanese aircraft. Of course, this global collaboration also brought Boeing substantial benefits, not only sharing R&D costs, but also gaining strong support from Japan's 2 major airlines, ANA and JL, for the 787. Every landing at Tokyo Haneda feels like hitting the 787's lair with no shortage of buyers. But problems followed. If everyone else has already built the aircraft, what does Boeing need to do? Why is this aircraft called the Boeing 787 instead of the Subaru 787? It's because when manufacturing aircraft, Boeing firmly controls 3 core tasks: first drawing blueprints, then establishing standards, and finally assembling and delivering, embarking on the journey. The first step is overall architecture design. Boeing needs to design the aerodynamic shape of the new aircraft, flight control layout, and determine key parameters such as range and passenger capacity. This phase often requires years of repeated demonstration and discussion, because it not only tests Boeing's technical capabilities, but also determines the new aircraft's market positioning, whether it's a flexible and efficient short-haul narrow-body aircraft or a long-range giant for transoceanic flights. Next, Boeing brings hundreds of suppliers into the same group and tells them the technical specifications and quality standards it needs, ensuring that all parts meet design requirements. Whether it's the fuselage, avionics, or a small screw, everything must be produced according to Boeing standards. For example, the 787 shell, although manufactured in Japan, has its specific dimensions defined by Boeing. When parts arrive at the final assembly plant, Boeing transforms into an orchestra conductor, coordinating the entire assembly process. Wings, fuselage, tail, landing gear step-by-step aligned, connected, and tested until the aircraft truly comes to life. However, final assembly is not the end point. New aircraft types must undergo comprehensive quality inspection and performance verification. Boeing must ensure that every component meets safety standards and that the overall aircraft performance achieves the initially set targets, fulfilling the promises made to airlines at the beginning. In addition, Boeing must also lead strict certification for airworthiness, organize test flights, collect data, submit reports, until it obtains airworthiness certificates issued by civil aviation authorities of various countries. After delivery to customers, Boeing's work is far from over. It must provide long-term customer service and technical support, including airline personnel training, flight control software OTA updates, and maintenance technical solutions, ensuring the aircraft remains safe, reliable, and economical throughout its entire service life. Therefore, even if a fault occurs in a supplier's components or software, the final responsibility still falls on Boeing. Because the certification is under Boeing's name, the architecture and interfaces are defined by Boeing, and verification and release are signed off by Boeing. With great power comes great responsibility. However, it's not hard to see that in the modern industrial system, aircraft manufacturers, including Boeing, Airbus, and COMAC, or prime contractors as they're called, no longer personally produce all components. So who is bearing the burden for them? Next, we proudly present the true heroes behind the aircraft. OEMs. You may have never noticed their names on an aircraft, but they very likely relate to your daily life. OEM stands for Original Equipment Manufacturer. In the aviation field, OEM typically refers to first-tier suppliers that provide complete systems for aircraft and master considerable core technologies. Some OEMs have tremendous bargaining power. If they throw a tantrum, Boeing and Airbus can't produce aircraft either. We're all suppliers. Why are you acting so superior here? We are solution integrators. Among all components, the most important is undoubtedly the heart of the aircraft, the engine. The world's three major aero engine manufacturers are General Electric, Pratt & Whitney, and Rolls-Royce. General Electric's predecessor was Edison Electric Light Company, which gradually expanded into medical, energy, aviation, and many other fields, with its logo widely appearing on industrial and medical equipment in our daily lives. In 2024, General Electric Group will spin off and separately list its aerospace and aviation business, highlighting its dominant position in the aircraft engine field. GE's representative work is the CF6 series, providing power for the Airbus A330 and Boeing 747-400. The subsequent GE90 is General Electric's masterpiece, powering the Boeing 777. Each one has a diameter larger than a narrow-body aircraft and produces thrust exceeding 50 tons, absolutely qualifying as an industrial crown jewel. Based on the GE90, General Electric developed the more fuel-efficient GE9X, applied to the Boeing 787 and 777-8. Let me explain to friends just getting into civil aviation why it's pronounced GN, because this symbol itself is a hyphen minus, corresponding to computer Unicode and civil aviation manuals, which translates to a connecting minus sign. A more intuitive method is to open your phone's browser now and type 737-8. You'll find that the first search result is not 737, but a calculator. If you verify this, please type "it really is" in the chat. Competing with GE in a wide-body aircraft sector is the British company Rolls-Royce. As the last glory of the British Empire, Rolls-Royce abandoned its labor-intensive and costly automotive business after bankruptcy and restructuring to focus on aircraft engines. Its signature skill is the unique three-shaft technology, which uses three nested shafts to keep different parts of the engine at optimal rotational speeds, improving overall efficiency. The first aero engine equipped with this technology was the RB211, which supplied the Lockheed L-1011 TriStar and the Boeing 757. This was later upgraded to the Trent series, including the Trent 700 for the A330, the Trent XWB for the A350, and the Trent 1000 for the 787. Rolls-Royce is currently testing a new generation of UltraFan as a future technology reserve, continuing to challenge GE's dominance. Compared to the previous two giants, Pratt & Whitney has been having a tough time lately. As a veteran manufacturer founded in 1925, Pratt & Whitney once dominated the civil engine market alongside Boeing's rise, but has now largely lost its share in the wide-body market. In the narrow-body market, Pratt & Whitney's PW1000G series is quite innovative in its design, but frequent malfunctions have forced many A320s and A220s to be grounded. I didn't ask you to stay functional forever. I'm no devil, but what's with the constant grounding? Pratt & Whitney is currently going all out to fix the grounded 1000G, but the road ahead remains long. In the narrow-body market, Pratt & Whitney's fierce competitor is CFM International, a joint venture between General Electric and the French Safran Group, whose classic product, the CFM56, has almost monopolized the narrow-body market over the past half-century with its ultra-high reliability. The new generation LEAP engine has further improved fuel efficiency, but as a brand-new model, its stability and ease of maintenance are still in the ramp-up phase. Even so, thanks to the tireless efforts of its peer Pratt & Whitney, the LEAP remains a popular choice for major airlines and has become the primary power source for the Boeing 737 MAX, Airbus A320neo, and COMAC C919. The history of the CFM56 and LEAP engines has already been released. Interested viewers are welcome to watch it. Planes not only need to be able to fly, they also need to be controllable, which brings us to avionics and flight control. They're the brain and neural network of an aircraft, providing pilots with sufficient information and feedback and transmitting instructions from the cockpit to the flight surfaces accurately. Currently, the global civil avionics market is dominated by three giants: Honeywell, Collins Aerospace, and Thales Group. People might have the stereotypical impression that Honeywell just makes masks, but in reality, they have an extremely broad presence in the avionics field. With deep expertise in sensors, Honeywell has mature products in cockpit display systems, autopilots, weather radars, and navigation systems, and their flight management systems cover over 90% of the global commercial fleet. On the Airbus A320, A330, A350, and Boeing 73. You can see its equipment on aircraft models such as the 777 and 787. Honeywell also operates a Boeing 757 test aircraft for testing and validating engines, avionics, and communication systems. On modern commercial aircraft, in addition to display equipment inside the cockpit, ground air connectivity is equally critical. Collins Aerospace, backed by the technological accumulation of Raytheon, the world's third-largest defense contractor, has brought high-speed data links and secure communication capabilities originally used in fighter jets and early warning aircraft down to the commercial aviation sector, enabling aircraft to maintain real-time data exchange with the ground even at 10,000 meters altitude, improving pilot decision-making efficiency. France's Thales Group hold an important position in the Airbus fleet. For example, the cockpit display and control systems of the A320neo and A350 are both provided by them. Its human-machine interface design emphasizes intuitiveness, allowing pilots to quickly access critical information even under high workload. Stepping out of the pilot's busy cockpit and opening that door, what meets the eyes of our audience is the cabin space that everyone cares about most. To make everyone sit comfortably, the cabin likewise concentrates a large amount of critical technology and the power of global supply chains. The three avionics giants we just mentioned, Honeywell, Collins Aerospace, and Thales Group, not only control the electronic equipment in the cockpit, but also deeply participate in the design and supply of cabin systems. From broadcast systems and RGB ambient lighting to motorized recline seats and personal entertainment systems, all rely on their technical support. For example, Cathay Pacific's latest Aria Business Suite is provided by Collins, with seats customized based on the Elements platform, capable of accommodating a 24-inch personal entertainment screen and featuring wireless charging. France's Safran Group is also an important supplier of business class seats. For example, the room business class on ANA's 787 is created by Safran. The main supplier of economy class seats is Germany's Recaro. That's right, the same Recaro that manufactures racing cars. In fact, the racing car connection is only a byproduct. Aircraft seating is their main business. In recent years, the Blade economy class seats, which have received mixed reviews, come from Recaro. While providing passengers with comfortable experiences, the preparation of in-flight meals is also important, which requires a fully functional and efficiently laid out onboard galley. Within limited space, integrating meal carts, ovens, coffee machines, refrigeration equipment, and stored cabinets requires extremely high demands on equipment modularity and lightweight design. Collins and Safran are likewise the main OEMs in this field. They not only need to meet passengers' diverse dining needs, but also help airlines reduce fuel consumption through weight-saving designs. In recent years, the popularization of onboard Wi-Fi has gradually broken the stereotype that flying equals losing internet connection. Panasonic Avionics is the leading supplier of onboard Wi-Fi, leveraging multiple communication satellites in geostationary and low Earth orbits to achieve global coverage across continents and oceans, enabling continuous internet access even over the Pacific or Atlantic, making it ideal for long-haul wide-body routes. Multiple well-known airlines, including Emirates, Singapore Airlines, and ANA, adopt Panasonic solutions. However, Panasonic is now facing strong competition from SpaceX's Starlink in the United States. Compared to traditional communication satellites, Starlink's network has lower costs, with even higher connection speeds and stability. Qatar Airways, United Airlines, and Hawaiian Airlines have already begun deploying it in their fleets, with speeds fast enough for passengers to smoothly stream videos in the air. It is worth noting that the choice of cabin OEMs is often led by airlines, with many facilities and configurations being optional. Even on the same A321, some airlines only fit over 100 seats, while Spring Hill can squeeze in 241 seats. Some business class cabins are just large sleeping areas, while others can provide you with a small suite. As for Boeing and Airbus, they are only responsible for completing the installation according to the airline's requirements. So next time if the airplane seat is uncomfortable, don't blame Boeing or Airbus. Direct your complaints to the airline instead. After all, whether the seats are cramped, the food is good, and whether there's Wi-Fi are all decisions made by the airline. While passenger comfort is certainly important, for a flight to be completed safely, the aircraft must also be able to take off and land safely on the ground. The landing gear and braking system must withstand instantaneous impact during landing and complete rapid deceleration at speeds of hundreds of kilometers per hour, which places extremely high demands on engineering design. The aforementioned Safran and Collins, in addition to being well-known in avionics and cabin systems, are also major suppliers of landing gear and brakes, and many aircraft models from Boeing and Airbus rely on their products. Meanwhile, over the past 11 years, Liebherr from Germany has gradually emerged as a rising star. As a company that started with construction machinery and engineering equipment, civil engineers should be familiar with this brand. Its yellow tower cranes and excavators remain active on construction sites around the world. Leveraging its strong foundation in heavy machinery manufacturing, Liebherr has achieved rapid breakthroughs in aircraft landing gear systems in recent years, particularly excelling in lightweight design and system integration, bringing lower fuel consumption and maintenance costs to the next generation of aircraft. In 2024, Liebherr presented a complete landing gear system at the Zhuhai Air Show, immediately becoming the center of attention. Of course, whether an aircraft can land smoothly depends not only on the landing gear and brakes, but also on the tires. Aircraft tires can maintain stable performance through hundreds of takeoffs and landings and friction at speeds of hundreds of kilometers per hour, which is truly a pinnacle achievement of materials science and engineering. Currently, the tires for global commercial aircraft are almost monopolized by two companies, Michelin from France and Bridgestone from Japan. What about Pirelli, which F1 fans are so familiar with? Unfortunately, Pirelli focuses on the racing and automotive markets and has almost no share in commercial aircraft. It is actually Michelin and Bridgestone that truly support global flights landing safely every day. Similarly, the names of these OEMs also appear on the scene. For example, the communication and navigation system is supplied by Collins, the environmental and surveillance system comes from Honeywell, the landing gear is manufactured by Liebherr, and the engines adopt CFM solution. But none of this changes the fact that the C919 is a Chinese aircraft. Because, just like the Boeing 787, Commercial Aircraft Corporation of China maintains the rights to overall design, integration, airworthiness certification, and final assembly and delivery, which are the key factors that determine which country an aircraft belongs to. Some people mock the C919 as just building a shell, but the 787 shell is made by Japan, its tail by China, its engines by Britain, with only 30% domestic content. Yet Americans have always considered the 787 a point of pride in American manufacturing. If China does not build the C919, then China's aviation industry will work for others for generations to come. In recent years, you can clearly see at the Zhuhai Air Show that the number of Chinese domestic suppliers is increasing, and they're beginning to compete on the same stage with established giants like Safran, Collins, and Honeywell, which is exactly the industrial chain upgrade driven by the C. As for whether C919 needs to be 100% domestically produced, the answer is obvious: no, and it's not realistic either. Any commodity must obey Hayek's invisible hand. Critics can't demand a market economy only when ordering a meal. To ignore so many mature OEMs is, to put it mildly, a violation of market principles, and to put it seriously, is to sacrifice passenger safety. However, compared to a small group of obsessed people constantly dwelling on domestic production, I believe most ordinary viewers care about only one thing. Since the C919 adopts the outsourcing model, just like Boeing, is this model actually safe? Indeed, the bizarre accidents that have occurred in Boeing in recent years, especially on the 737 MAX, have put the outsourcing model in the spotlight. Many people have therefore simply attributed the 737 MAX tragedy to outsourcing. But in my view, outsourcing is not the original sin. Relinquishing control is the disaster. The most typical example is the MCOS system, which is a key algorithm controlling aircraft attitude, should have been developed by Boeing's core engineering team in Seattle. However, to compress costs and timelines, Boeing outsourced some development work to Indian companies HCL and Cyient. These external teams generally lacked experience, had lower salaries, and quality control was inadequate. More seriously, under tremendous pressure to catch up with the A320neo, Boeing failed to correct flaws in time, rushed the aircraft into service, and ultimately caused a major disaster. Similar hidden risks also appeared in the manufacturing process. For example, the 737 MAX 9 cabin door incident. The problem actually wasn't with Boeing, but with supplier Spirit's assembly defects, yet Boeing ultimately bore responsibility because the prime manufacturer is always ultimately responsible at the system level. This sense of loss of control forced Boeing to make a painful decision. In 2024, Boeing announced it would spend approximately $4.7 billion to repurchase Spirit. This company was originally Boeing's fuselage business, spun off in 2005, but is now being reacquired due to frequent quality incidents. By comparison, Airbus's approach appears more robust. As an enterprise founded by multiple nations, Airbus also extensively uses outsourcing, but has established a rigorous coordination and standardization system. An Airbus aircraft is often manufactured in segments by Germany, the UK, and Spain, then shipped to Toulouse, France for final assembly, where it undergoes strict system integration and verification on the assembly line. In recent years, the participation of Chinese Shenyang Aircraft and Airbus's Tianjin factory further validates the stability of the transnational collaboration model. From the A220 to the A350, Airbus aircraft quality is well regarded. However, you can't walk by the river without getting your shoes wet. Airbus has also made some minor mistakes. For example, when manufacturing the A380, French and British engineers had already started using Qiddiya V5, while German and Spanish engineers were still using Qiddiya V. Although the name is the same, anyone studying engineering knows these software packages have terrible compatibility, which ultimately led to cables being unable to connect during the final assembly stage, severely hampering project progress. In recent years, Airbus also failed to manage quality issues with Pratt & Whitney's PW1100G engines, resulting in approximately 300 to 500 A320s being grounded each year, staying immobilized for extended periods. This shows that outsourcing itself has become the norm in the global aviation industry. What truly determines success is not who manufactures the parts, but whether the prime manufacturer can maintain design authority, strictly control quality, and effectively manage the vast supplier ecosystem. This is the soul of an aircraft. Due to video length constraints, the OEMs introduced in this episode represent only the tip of the iceberg in a vast supply chain. In fact, behind a modern airliner often stand hundreds or thousands of suppliers, including deeply established international giants and emerging enterprises working hard to rise. Their names may not directly appear in your flight booking app, and passengers may not pay particular attention to them. But every smooth climb and precise landing depends on their silent dedication. On the other side that passengers can't see, the cooperation and competition between prime manufacturers and OEMs also constitute a silent struggle, featuring both tales of win-win collaboration and undercurrents of conflict. Both glory from technological breakthroughs and crises from loss of control. One could say that it is precisely this love-hate relationship that drives the continuous evolution of the global civil aviation industry. So the next time you sit in the cabin and gaze at the wings outside the window, you may better appreciate that the aviation industry has never been a one-man show of any single nation, but rather the crystallization of global industrial cooperation.